Okay, so this is module 3 for the general linear model, um, MRC and Anova. So there's a lot to talk about, so I'm going to get started. So what is the general linear model? So it's a tool. It's used to analyze statistical data called general because it encompasses multiple types of methods. So regression and correlation, known as MRC, multiple regression and correlation, and analysis of variance, so ANOVA. The linear part indicates that it's additive. And the formula for the general linear model kind of looks like this. This y equals the dependent variable. The b represents the population, which is usually, it's actually a vector of weights that's assigned to our predictors. Our predictor or our predictors is our x, and the epsilon represents either error or residuals, depending on what form you're using, either MRC or ANOVA. And we're going to discuss that a little bit further on. So to talk a little bit more about the MRC model, I've listed some of the details about the assumptions related to this model. The key takeaway here is that MRC revolves around measures of association, such as correlation. Multiple regression helps us understand the correlation between many different predictors, modeling everyday life and studies a lot more accurately. With the MRC, you can have more predictor specifications. It allows you to calculate and model main effects, interactions, and rectilinear and curvilinear relationships. And then here I've kind of listed the assumptions or the rules that you kind of have to follow for MRC. And for ANOVA, so ANOVA stands for analysis of variance, and it does, just what the name implies, it's going to take a closer look at our variances. So we use F-test to calculate the ratio of variances, which represents our signal to noise ratio. ANOVA also follows a set of assumptions. They're really similar actually to the MRC model, except this one really focuses on errors. And those are the crucial assumptions. They need to be independent from each other. They need to be identically distributed, and that distribution needs to be normal. So comparing the two, in MRC, those covariates help us explain the dependent variables, or our y's. How it differs is really important. So the E is seen as a residual, not an error in in MRC. And we can capture just a lot of information by analyzing these residuals. However, in ANOVA, we don't try to explain error. They're just random, uncorrelated. Um, and why MRC and ANOVA kind of fit together within the general linear model is that there's a conversion point between the two. You can kind of convert t-tests to correlation coefficients and vice versa. And that's going to bridge the two different methods. You can easily jump between the two if you kind of know how to do that. Okay, so we're going to take a look at the data that we're using today. So we have our y's are going to represent our dependent variables. We've got 4 of them. Our x's are our covariates, and there's 7. And then our factors are at the end. The F represents our factors, and we've got 8 of them. We're not going to use all of this data. I'm just going to select and run a few of these just to analyze them further. So starting with the MRC model, after a couple of test runs, I decided to go for X3 and X5 as my predictors. And also I used the interaction between the two to run my analysis. Our critical p-value is a classic, greater than 0.05. And both X3 and X5 are significantly different from 0, which means that the mean for X3 and X5 is not 0. So taking a look at X3, the estimate are our B's, and if you divide that by the standard error, you're going to get the t-value. And the t-values are ratios of signal to noise, so essentially testing if the signal is strong enough to outweigh the noise. And in this case, for both X3 and X5, they are. That's why we're seeing higher t-values and lower p-values. So for X3 and X5, we can reject the null hypothesis. However, we fail to reject the null hypothesis for the interaction between x3 and x5 because our p-value is 0.10, which is, greater than the 0.05 critical value. Next, we're going to run some MRC diagnostics for the data that we picked out. So our variance inflation factor is going to measure the amount of multicollinearity in our analysis. So multicollinearity exists when our independent variables are shown to correlate with each other. Our VIF measures for our variables are slightly greater than 1, our x5 being the smallest, meaning that there is some moderate correlation between our variables. We're going to run some further diagnostics. So we're going to look at the rectilinear bivariate relationships between the two using series plots. They're useful because they allow us to partition the primary covariates, and we can see if they're rectilinear with our variables. So we partition our two variables, x3 and x5, and we want to see if they're rectilinear with our dependent variable y1. So we want the purple line to follow the blue dotted line as close as possible. And we see some slight curves, particularly with x3 at the far ends. But for the most part, the purple line aligns really nicely. And we can see that both x3 and x5 are rectilinear with our dependent variable of y1. If we had heteroscedasticity, this would show more error and more, the purple line would deviate a lot more from the blue dotted line. Next, we're going to look at our independence of residuals. So this is a residuals versus a fitted plot. We're going to compare our y-hats and our residuals. So our plotted line is very horizontal and close to our predicted line, which is ideal, and that's what we're looking for. We're looking for some symmetry around 0. There appears to be some influence from some data points, specifically the one labeled 30, but it's somewhat minor, so I'm really not too concerned about it. We should not see a lot of relationships or correlations. We want our residuals to be independent of each other. And I think this looks pretty good. So yeah, our line is very horizontal and really close to our dotted line. Next, we'll look at the normality of residuals. This is the QQ norm plot. This plot breaks up distribution based on expected and standardized results. The tails show a bit of deviation from our expected variable, but overall the distribution would be considered pretty normal. The lack of an S shape from our plot points also indicate normality. So again, these are looking pretty good. Now we're going to take a look at homoscedasticity. This scale location plot takes the absolute value of the square root of our standardized residuals to get smaller metrics of residuals. Heteroscedasticity is a violation of one of our MRC assumptions that we talked about earlier. So we're looking for homoscedasticity, which would be indicated by our values being evenly distributed around our line of best fit. Okay. Now we're going to look at the influence our outliers might have. We're going to look at our residuals and trying to look for outliers that may have some influence or leverage on our plot points. So 11 and 14 seem to have some influence. It pulls our line down a little bit. So then we're going to look at our Cook's distance, and it also shows that 11, 14, and 26 have higher Cook's distance and applies undue influence on our results. But I would say it is pretty subtle. We're going to move on. So we ran some diagnostics tests on our plot points for MRC, and we found that our X3 and our X5 have significant results. We were able to reject the null for both, but not for the interaction, possibly due to multicollinearity. There's minimal evidence for heteroscedasticity based on our diagnostic scale location figure and the series plots we did. And eliminating predictors 11 and 14 specifically would really help explain our dependent variable with a little bit more confidence. Overall, I don't think this was a bad test at all. Next, we're going to try Anova. So our mean square is going to represent our variance. And if you divide the mean square and within a factor, you're going to get your F values. So in MRC, we use covariates. In Anova, we're going to use factors with the assumption that they're orthogonal. So I'm using F2 and F6 to predict the same dependent variable, which is Y1, the same one I used for MRC. F2 appears to be the only significant value because its p-value is 0.02. F6 falls above the 0.05 critical p-value. So our between group difference used our sum squares and our mean squares divided by the degrees of freedom. So we get all this information. So if you can take the mean square of factor 9.884 and then divide that by the residual mean square, so 1.617, and we get the F value of 6.114, then that's going to give us a p-value of 0.02. So we reject the null hypothesis with F2. For F6, we fail to reject the null because the p-value is greater than the 0.05, and the interaction between the two is also non-significant. So we're going to look at the independence of our predictors and run some diagnostics tests for Anova. We don't really have a balanced design, it seems, and we have a small sample size as well. That can affect the independence of our predictors. So this could indicate that Anova just might not be the best test to use for our data, where we're going to analyze a little bit more. So looking at the homogeneity of variances, the variability of two of the medians is somewhat large, and the other two look okay right here. These kind of seem to vary a lot. We're going to do some further testing and use the Levene test, which I have over here. And we're going to continue to look at the homogeneity of variance. And we can see that our p-value is 0.243. So we failed to reject the null. Also, the DF shows 5, which indicates that either F2 or F6 have multiple levels within its group. And looking at some more stuff, we're going to look at the independence of our residuals, and residuals seem to be really close to the 0. This it seems to show that our residuals are mostly independent from each other. We're going to do another normal QQ plot, but for ANOVA this time. There are some deviations at the tails from the expected values, but they're all the plot points are pretty close to the line, and it appears normal. So there's a minimal S-shaped curve, so our residuals appear to be normal. We're going to look at the homoscedasticity. Some of our residuals in our homoscedasticity figure appear far away, but they're not consistently moving farther away as our fitted values increase. So we may not have heteroscedasticity in this model. We've got to look at some more diagnostic testing. So our outlier influence, case 2 for our outliers appears to have some influence on our data. I wouldn't say that's insignificant. It looks to be a pretty large influence right over here. So maybe if we did some further testing, we would remove that variable and see how it affects our plot points. So what can this mean? So our F2 was our only significant predictor with a p-value of 0.02. F6 and the interaction of F2 and F6 were non-significant. So we failed to reject the null there. The unbalanced design really did not help with this study. The residuals appeared to be independent though, and there is some evidence for heteroscedasticity, specifically the scale location figure showed that. There's also evidence for influential observation. So case 2, that seemed to pull our, have some influence on our outliers. And then overall, it seems like the MRC model is a little bit better to use because we have a slightly unbalanced design. Also, here we have the hand calculation for ANOVA and MRC as well.